the same information all at the same time. It will be the official announcement, and that will come out well in advance of exam 1 so that you have time to prepare and, of course, ask us any clarifying questions if you have them, okay? So don't fret. All the information will come out shortly. Okay. We talked last time about hypoeutectic regions, and now we'll talk about the hyper or greater than eutectic compositions. So here is the lead-tin phase diagram again, outlining the phase fields that you see here, the liquid phase, the single phase alpha and beta, in which in alpha you have limited tin solubility into the lead system. And here lead is the alpha phase, and that would be, FCC. But if you didn't know the crystal structure of alpha, you wouldn't get it from here, right? Because all this phase diagram is telling you is that you have alpha phase. And similarly, on the right side, so here you have limited solubility of lead into tin. And in fact, you have even less solubility of lead into tin, given that here it's 97.8 weight percent tin. So you have a little less than 3 weight percent lead. Okay, so that's quite significant. There was also a question from this side of the room about, do all of these eutectic phase diagrams look graphically similar? The answer is yes. That's what I said last time, in the sense that there should be a defining eutectic point where you have a depression in the melting temperature of the system versus the single component melting temperatures of either metal or ceramic system. But you can have, not only can you have this sort of phase diagram where you have limited solubility, but you can have actually no solubility whatsoever. And the difference there would be, if you have basically no solubility, you wouldn't have this curve, this solvus right here. What you would have is actually just a straight line. So graphically, what that would look like is something like this, where let's say here's composition, here's temperature. You could have something that looks like this. So this line right here is your isotherm for the eutectic temperature. Here's your eutectic point. But on either side, it's just a straight line. So what that's telling you is component B going into A and vice versa, it is just nearly impossible, if not just impossible. Okay, statistically, everything's always nearly impossible. But what I mean is, like, physically, it's going to be very difficult to even get point something weight percent of A into B and vice versa. So graphically, yes, they are similar in that you need to have this distinctive eutectic point, but the sides may differ a little bit. For this particular system, lead tin, or the other example that you saw, copper silver, there's some limited solubility where the two, you can have a single phase on either side, but that might not always be the case. And you'll see that with some intermetallics that we'll talk about in a little bit. Okay, so there is an asterisk to my answer from before, while true. Okay, here are some micrographs of the hypoeutectic region, the eutectic region, and let me switch over to laser pointer. So the hypoeutectic region, where you see primary or proeutectic alpha that come out from this temperature. So if you're at this particular composition, you come down, you form some of these primary or proeutectic alpha blobs, and then the remaining liquid will just go into eutectic alpha and eutectic beta. So if you had to draw your tree, let's switch back to pen. So anything where you go from liquid and then liquid to alpha, and any remaining liquid will go into eutectic alpha and eutectic beta. Okay. And then similarly, on the hypereutectic side, you have liquid and then you have primary or proeutectic beta blobs that you see here. And then any remaining liquid, once you pass the eutectic temperature, will give you eutectic alpha and eutectic beta. And that makes sense since you're in the two-phase region. Okay. Any questions on the recap thus far? Yes?
So those,
I'm sorry?
those blob areas, they're at what point on the...
These blobs and these blobs?
Yeah, where would they be on
This particular all of these microstructures are after the eutectic temperature, like below the eutectic temperature as you're solidifying. So high temperature, once you pass TE, then you can get these microstructures. The primary or proeutectic alpha or beta form before. So once you encounter this liquidus right here, if you're in the hypoeutectic composition region, you immediately start forming these primary blobs. So they form, so the microstructure is, if let's say you're in this region here, they form immediately, right? Once you hit the liquidus, you start solidifying some alpha. They form. They don't go away. They stay there. And then you continue your solidification, and right after this eutectic temperature, any liquid that remains will transform into the lamellae that you see here in this micrograph. So all those stripes. Now, the primary alpha and primary beta don't form at a specific composition, and that is this composition right here. That's your eutectic composition. So if you are right at 61.9 weight percent tin, and you start to solidify, when you hit this point, 3 phases exist: liquid, alpha, and beta. Right below that temperature, upon further solidification, you will have this structure right here, and you will only have the lamellae or the lathes or the stripe type features because of the atomic diffusion of both lead and tin.
So the blobs basically start in liquid form?
They start right in this 2-phase region right here. So if you happen to be at this composition, right, above the solubility limit, above the concentration, or the composition is higher than the solubility limit, the max solubility limit of tin into lead right here. So if you're anywhere here, you're going to start seeing these primary. Now, to follow up your question and to be more specific, we don't really call these blobs primary if you happen to be in the composition region of, let's say here, up to this concentration or composition, okay? I'll call this C1. If you're up to C1, typically people don't call it pro because there's nothing to distinguish upon solidification. There's nothing to distinguish the pro from anything else, right? I mean, technically you could, because pro means before. So proeutectic means before the eutectic. If you're higher than the eutectic temperature, sure. But once you solidify, so you go from liquid, and then once you solidify in this C1 region, you get to, if you zoom in on this particular area, you'll see a little bit where you're in the liquid plus alpha phase field. So sure, you'll have something that looks like, at, let's say, T1 here. So C1 and T1, you'll start to see some alpha, sure enough. Okay. But then upon further solidification to here, and then all the way down to 50C, where the data ends, you'll end up with just so C1, T2, you end up with these alpha grains that have, the blobs have grown and grown and grown, solidified, and then of course you have all these grains of just alpha. So here, you wouldn't call them pro anything because there's no eutectic to distinguish, you know, it's like saying something very specific when there's nothing to distinguish it from. It's a little bit redundant.
So if you're going to take a screenshot of the lavender area and the area right below it,
Yeah.
what would you see?
So this lavender area below C1, this part right here,
Yeah, so when you're in there, you get
you only get alpha. So alpha already signals to you that you're solidified. So then you would only see this for that little rectangular area that I just marked out.
so when you went below, you could get the line shown.
No, you'll never get eutectic because if do you mean like these stripe lines or these grain boundary lines?
Yeah, I guess I'm just curious about the line separating lavender from the area right below, what changes.
Oh, you mean this right here, the solvis?
Yeah, what happens between
Yeah, so as soon as you cross this boundary, you're really going along the x-axis, right? You're introducing more, right. So if you're just in here, well, so you're confined in phase field, right? So if you're in this space and you're between, 50C, and obviously it's a gradient, it's increasing. If you happen to be here or anywhere in this purple region, you will have only alpha, right? There's no beta in sight. Now, when you cross the solvis, then you are in a two-phase region. But you don't necessarily have eutectic yet if you're below, I'm going to call this C2, okay, 18.3. If you're below the maximum solubility, particularly it's 18.3 in this case. So if you're below C2, so if your composition is less than 18.3 weight percent of tin, and you are here, so if you're between here and here, you will have some beta, and what that looks like is C2, let's say you're at T2, let's say you're, well, let's pick a different, yeah, T2, let's not be so extreme. Let's call this C3. So if you're at C3 and T2, you have alpha because you've already solidified alpha, right? So your alpha is already formed. But now you have an emergence of some beta. And that emergence looks like little, so here's all your alpha grains. That emergence shows up as, could also be at the grain boundaries, little specks of beta. It's not really eutectic, right? Because it's not in the eutectic region. It's not in the hypo or the hyper. Also, if you look at your lever rule, right, here, if you're here, how much alpha are you going to have? So you draw your tie line. Okay, that's extending beyond it. Okay, I'm going to start erasing some things for clarity. If you're here, I'm going to offset a little bit. If you're here, if you draw your tie line, right, this is alpha, this is beta over here. If you take your weight fraction of beta, right, that's going to be this little section divided by the entire length. So how much beta are you really going to have? You're going to have little specks of it, right? So that's how you can think of it. Yeah. So where's the middle structure microstructure coming from? This is exactly at 61.9 weight percent tin. Do you see how there's no primary anything? Either of the primary? That only occurs right at 61.9 for this system. So right at the eutectic composition. What temperature? This has to be below your eutectic temperature, right? It has to be below the solidification. If you're right above it, you still have some liquid. So then you have to represent that somehow, little blobs of liquid or whatever. So all these microstructures are at temperatures below that of your eutectic temperature. Okay. Dare I say we can go on? Okay. This is the intermetallic that I was talking about. So we've had examples where you have single component systems like magnesium and lead. So that's nice. And on the left side, you see a single phase area here. Alpha, we see our reliable eutectic point where liquid goes to alpha and something else, another solid phase. Before we called it beta. This time it is not beta because beta is over here. This little sliver right here is beta. So if you're in this compositional area space right here, right, when you draw your tie line, let's say you're here, you hit this composition, C alpha, and then you can go to the right and you actually hit the intermetallic, a compound that is magnesium to lead specifically. That's the stoichiometry. So what you have is actually the composition of magnesium to lead. So to apply the lever rule, it's the same technique, right? You have some fraction, let's say if you're calculating weight fraction of alpha, you take that line divided by the entire length right here, okay? So you treat it similarly, but your C magnesium 2 beta is 80. You just read it off of the plot here. It just goes straight down. So you can have asymmetry in your eutectic diagram, not a problem, okay? But the technique is the same. Just read your composition off of the phase diagram. It doesn't have to be a single component. It doesn't have to, well, magnesium 2 lead is treated as a quote-unquote single component in this case, but it doesn't have to be just one element is the point. Okay, so you still have the hypoeutectic region here. So this is CE. Then you have hyper here. You'll notice that this phase diagram has two eutectic points. There's one here, and there's one here. Okay, so it's absolutely not a problem. In these cases, one would just take the phase diagram piecewise, right? So you can treat everything to the left of this intermetallic as one, and then you can take the other eutectic point as sort of another phase diagram. So you can just break down a phase diagram. It doesn't have to be overly complex. Okay. And so here you see the different microstructures very similarly for how you would go about drawing the microstructure for a region that goes through a single phase field and then end up in a two-phase region. So you could see in the orange specks here how the magnesium 2 lead could form once you solidify alpha. Okay. And then similarly in the hypereutectic region of 70 weight%, you go from liquid, and then you have the proeutectic magnesium 2 lead, and then you get the stripes. So pretty similar, nothing different, okay? Although the difference is the resolution is quite poor in this particular figure, but that's about it. Okay, so we're going to go on and just talk very briefly about different reactions that you could also see on a phase diagram. So here is a copper-zinc phase diagram going from 0 to 100% atomic percent of zinc on the lower x-axis. Temperature is still on the y-axis. And so you could have eutectoid that we'll talk about, where you have a solid going to two solids. In this particular case, it's delta going to gamma and epsilon. Okay, so you have this delta region right here. You can start out there. And then once you pass this point right here, you get into gamma and epsilon. You can have what's also called a pereutectic reaction where you can have one solid and a liquid, but instead of transforming into two solids, you have transformation into a solid phase. So that's given here where you have delta plus liquid, so you're in this region right here, and then you transform into an epsilon region. Okay. So as you can see, phase diagrams can be complex, but the lever rule will take you far. We're not going to go into great detail in regards to hypereutectic phase diagrams or hypereutectic reaction itself, but you should know that it exists. Okay, so this is just the zoomed in area of the same phase diagram outlining the hypoeutectic and eutectoid, although that's misspelled. Okay. A small word about coring and how you can have non-equilibrium microstructures. Basically, if you cool too rapidly, you're going to have a gradient of the compositions that you see in the microstructure, right? So when we were talking about the blobs before, right, we said, okay, you cool very slowly and then you get some solid area in liquid and then you just have finally liquid. Okay, but if you go too quickly, you can have this gradient where the different shades of blue are indicative of the different concentrations of your components. So in this example, it's nickel and copper again. So instead of expecting one overall concentration or composition in the blob or in each grain, you'll have this gradient. So this is useful for you to know because if you are cooling too quickly in some sort of manufacturing condition or application, your material will not have the same performance as you would expect, right? And one of the ways you would know that is by doing a variety of mechanical properties tests that we'll talk about in Chapter 7, which is the next module on mechanical properties, like and testing things like hardness and other properties. So you can get that, and over time you'll see if you change your cooling rates to the point where you don't see a change in the property, then you know there's probably not a change in the concentration gradient. And so your material will fail or not fail accordingly. Okay. So we also won't focus too much on this, but you should know whenever I talk about equilibrium, I'm talking about some extreme end where you've waited for your material to cool at some slow rate enough that you can trust that it is at thermodynamic equilibrium. Okay. This is particularly important in welding because sometimes you can apply heat, and then when you remove the heat, you know, there could be where the joints are, you know, where the welds are, you can definitely see some gradient. And of course, the fundamental engineering aspects of studying these welds has massive manufacturing implications. Okay, and knowing how the concentration gradient is occurring, you know, has quite economical implications there. Okay, so we'll talk about the iron-carbon phase diagram, and then we'll dive into some example problems in your supplemental PDF that I uploaded. But for now, we're going to stick with this slide deck before we jump over. I also have an example of hypereutectic lever rule practice. And so after I talk about iron-carbon phase diagram, if there's time, I'll take a poll as to whether or not the class is interested in doing another example, or if you would just prefer to move on to the eutectoid example, okay? But after we talk about iron-carbon phase diagram. We've seen this plot, this diagram at the beginning of this module. It obviously has huge industrial implications, which is why it's often studied. Just to review, here you have on the y-axis temperature. X-axis is weight % of carbon. What you'll also notice is this particular diagram cuts off at 6.7 weight% carbon. And that's because what is of interest for steel ends about right here at 2.14 weight% of carbon. Above that, that's cast iron. And below that composition is steel. And so we'll be focusing on the steel region. So this phase diagram obviously extends much farther to the right than just 6.7 weight%. Obviously, you can go out all the way to 100% weight% carbon. But in terms of industry and manufacturing, this area is what we're interested in, and also this area. It also makes the diagram a little bit more tractable to work with. So you'll notice that things resemble that of a eutectic phase diagram, and in fact there is a eutectic point. That would be right here, where you have liquid going from liquid to gamma plus iron carbide, Fe3C, or cementite. So here you see the property of cementite. It can be quite brittle. It's hard, so it's resistive to indentation, but it's quite brittle. And here's the crystal structure. It's orthorhombic. So you see the iron and carbon atoms packed into the unit cell there. What's also of interest to us are the BCC and FCC phases. And so to remind you, the iron wire demo, we just focus on, I'm going to switch over to blue, mainly for distinction. So you'll remember that we focused on this line right here where we just have iron, okay? And we went from BCC alpha, so that's ferrite, to gamma, or FCC iron, or austenite, okay? So there you see alpha, and then this delta region right here. So we went from solid to solid. And then upon cooling, we went from austenite to ferrite, or FCC to BCC. So at no point do we go through the liquid region. And so if you're at this composition, let's say at 0.76 weight% carbon, and you're cooling down, you're going through the eutectoid reaction, or the eutectoid temperature, and you'll get a gamma going to ferrite plus cementite. And that's denoted here for you already. Okay? Okay. So, solid to two solids, eutectoid. So that is outlined here. And the microstructure looks like this, where you have grains of gamma right here. Okay. And then you get two phases, alpha plus Fe3C, or alpha plus cementite. And you notice that the microstructure is quite similar to the eutectic microstructure, where you have these lamellae right here. Okay. But let's look at the fraction of alpha versus Fe3C. If you're here, right, you're much closer to the alpha phase. So one would expect that you have a lot of alpha. So the white parts would be the alpha, and you would have thin areas of Fe3C or cementite in between those alpha. Okay? So it's nowhere near 50-50. Okay? So that's what you would expect. And you would have to actually magnify, use an objective lens with greater magnification to really magnify the area to even see those areas of Fe3C. Okay? So this is what we'll be concentrating on for the rest of the module. Okay. So we have similar terminology So hypoeutectoid, you're going from gamma to gamma plus alpha in this two-phase region right here. And then right below the TE now being temperature of the eutectoid reaction, whatever gamma that remains that has not transformed to pro-eutectoid alpha will turn into eutectoid alpha and eutectoid Fe3C. Okay? So very analogously to that of eutectic phase diagram. And then for hypereutectoid, so you're greater than 0.76 weight percent of carbon up until the 2.14 composition, you'll have gamma or austenite, and then you transform into gamma plus iron carbide or cementite or Fe3C. And then what doesn't turn into pro-eutectoid Fe3C, that remaining gamma will then transform into eutectoid alpha and eutectoid Fe3C. Okay. So you can imagine the microstructures are going to be similar with these blobs and the striped layered type structure. Okay. Okay. And that's exactly what we see. So for hypoeutectoid steel, we can use the same lever rule. So if you're in this region right here, up until 0.76 weight percent carbon, if you're there, and let's say you're, that's your composition and temperature, when you draw your tie line, okay, that's to your right, that's to your left. And so the weight percent of alpha is just C. Oh, that should be Fe3C, actually. Yeah, that should be Fe3. Oh, sorry, that should be here, yeah. That should be the C gamma minus the C naught. This is your C naught. Although, hold on, let me check. So you take the weight percent of carbon. Hold on, let me see if there's a typo in this. You take this distance and you divide it by the entire length. Okay. The microstructure looks like this, where you're at 1,000 degrees C, you have all of gamma already solid, and then you'll have the emergence of the pro-eutectoid alpha, and that starts to grow right at the grain boundaries. And then they'll continue to grow some more in the blue regions there. And then eventually at 726, so right below the eutectoid temperature here, you'll get the stripes. Okay, so you still have your pro-eutectoid and your then your eutectoid microstructure. Okay. Okay, so I think we should probably do an example to actually practice that. So let me go to that example. That will be your, this is hypo. So let's go to the example in the supplemental PDF. So if you happen to have a C naught of 0.24 weight percent carbon at 725 C, so that means you've just solidified below the eutectoid temperature. So 0.25 is somewhere here, about a quarter, so you're about here. Okay. So if you want to know what the compositions of the alloy are, and also C alpha and C Fe3C, okay, we can just draw the tie line. So CFE3C is just 6.7 weight% of carbon. C alpha hits it right at, it's difficult to see, but it's outlined here, that C alpha is 0.022. All right, I'm going to write it up here. And of course, your C naught is that, okay? So then, similar to the eutectic phase weight fractions or mass fraction calculations of your two phases at 725 C, you can calculate what those phase fractions are by using the lever rule. So I'm rewriting that so that we have the numbers. So the phase fraction of alpha we anticipate is going to be something ridiculously high, right? Close to 1 or close to 100%. And we can just see that graphically. Okay, let's look at it graphically. If you're here, you're really close to the alpha phase, right? So you anticipate you're going to have mostly alpha, just graphically speaking, before you even crunch the numbers. So when you actually crunch the numbers, okay, I plug in the numbers that I read off of the phase diagram. I get so I'm getting a 0.967 weight fraction of alpha. Okay, all of the alpha that I have in my system. I'm not talking about just pro-eutectoid alpha or eutectoid alpha, just all the alpha in the system, right at that composition and temperature, is 96.7%. So it dominates, it's going to dominate your microstructure. And then the little cementite that I have, well, it's 1 minus that. Or if we put in the numbers, right? So you could see the amount of Fe3C that you have in your entire system based on the lever rule is quite insignificant. Okay. Now, oh, was that a hand? Oh, just stretching. Okay. Now, we've determined how much alpha and how much Fe3C there is, period. Right? And we know that from this phase diagram, because we're here in the two-phase region. So we've accounted for all the alpha and all the Fe3C. But we know that when you went from gamma, some of that gamma transformed into pro-eutectoid alpha. Okay, so now we want to know how much of that transformed into the pro-eutectoid alpha above the eutectoid temperature. And so we can apply the lever rule again, but in a limited space. Okay, so we can apply the rule again, but in this region right here, right before you go below the eutectoid temperature. And so if we do that, our limits are going to be the liquidus line and this solidus line, or sorry, not the liquidus line, the solvis and another solvis. So it's just separating solids. So you hit this right here, which is and this line right here, which is still 0.022 weight% carbon. Okay, so you can use the lever rule in the two-phase region where it's alpha and gamma. So pro-eutectoid alpha and gamma. And so if you do that, you can determine the weight fraction of pro-eutectoid alpha minus your composition divided by the entire length. Oops, sorry. That is not how one does subtraction. Okay, so that's how much pro-eutectoid alpha you have. So let's do a sanity check before you continue on. Well, 0.705 is less than that of 0.967, right? So the amount of pro-eutectoid alpha you have should be less than the overall alpha that you have, because the overall alpha that you have is both pro-eutectoid alpha plus eutectoid alpha. Okay. Now, before we called the eutectic microstructure as these lamellae, stripe kind of microstructure. Here we call this microstructure perlite, and the stripes give the material sort of like a pearlitic sheen under the microscope. So clearly, this is a historic term. This is not to be confused with perlite that you use in your gardening materials. That's obviously a ceramic and very different than that of this microstructure, okay? So perlite here is in reference to the microstructure that you see, or the microconstituent that in the microstructure that you see. So it's just a historic term. So if we plug in the numbers there, we get that to be the amount of perlite, okay? So your perlite has both eutectoid alpha and Fe3C. Eutectoid Fe3C, okay? Okay, so then you can do a check. I did not leave space for a check, but you can do a check similarly to how we did the check for eutectic phase fractions, okay? So we know that there are 3 microconstituents, right? And so we can say, okay, how much alpha do I have overall? How much of the eutectoid do I have overall? And so if you add pro-eutectoid alpha plus the amount of eutectoid alpha plus the amount of eutectoid beta, or sorry, in this case it's cementite, you should get to 1. Okay? So I would just do that check. Questions so far?
Can you explain where the 0.76 came from?
Yes. Can I explain where the 0.76 weight percent carbon came from? That is the composition of your eutectoid reaction. And why you need that is because you are trying to determine the amount of pro-eutectoid alpha in your system. Okay? So you are trying to determine from your microstructure, if this is here, you're trying to determine how much. So here you start off with this gamma. Okay, so this is all gamma. And then you have the emergence of some pro-eutectoid alpha. But how much of this do you have in your system? Okay, so this forms when you're in this 2-phase region right here. And then after that, below the eutectoid temperature, you get the LAS. Okay. So your gamma then transforms into eutectoid alpha, and also, actually that should be the white part. And then the small blue line should be eutectoid Fe3C, and this is pro-eutectoid alpha. So why does this matter to you to know where the 0.76 weight percent carbon is? Because the 0.76 weight percent tells you how to determine the phase fraction of these blobs of the pro-eutectoid alpha. You need that information to use the lever rule right here. Right here. Okay? This is your composition, 0.24 weight percent. You're right here. Okay? So then if you draw your lever rule, you have one component on your right, one component on your left, and that should hit your eutectoid composition. All right, I think the thumbs up is indicative of a satisfied answer. Yes?
What is the eutectic alpha and eutectic alpha?
This, okay, what is the eutectoid alpha pointing to? It is pointing to this white space right here. This is pointing to all the white space. And eutectoid Fe3C is pointing to these lines specifically. And I draw them as lines because of the phase fraction. I have 0.033 of Fe3C, eutectoid Fe3C, right? So I'm not going to draw them as, you know, big lines like this, because that looks sort of like 50-50, right? I'm trying to be more representative of the phase fraction in my schematics. That's all. Yes?
So where does perlite exist on this diagram?
Perlite exists as a microstructure in the hypoeutectoid region and hypereutectoid region.